Okay, we might do a quick sound check. Can everyone hear me okay?
Yeah.
Okay, thanks, Amy. And yes, I just saw that email as well, Wayne. In the rush, it's easy to do typos, but that's a funny one. Okay, so this week we've got 5 people now, so 4 people plus me. And so this week we're looking at lists and algorithms. Okay, so last week, had a good week last week. We spent the whole week on assignment 2 sort of related topics. We read the spec, highlighted keywords. We didn't get to do a storyboard in the end, so I'll take that out. I wanted to, but we never sort of got there. There's some screenshots in the spec, and I think that's all we really needed. We talked about model view controller, which is a question Wayne had from a couple of weeks ago, which is very relevant. It's not a topic we officially cover, but it's the way we sort of think about developing apps in this course, especially later on in the later half of the course. And then we looked at assignment 2 topics like exploring generics, discussing a strategy for dealing with the array list class and making it generic, and then file IO and typed files, things like that. And then we developed the GUI in class, and we had those 4 files there, and they're all on my GitHub if you want to get hold of those. Of course, they're on my GitHub. Okay, so this week we'll talk about linked lists, algorithms, collections, iterators, sorting, searching, binary searching, big O. So not all these topics are in the slides, but they're all related, and they should all be in the slides. Okay, so we'll go through things anyway. So big O is not mentioned in the slides, but it should be. Okay, so a little bit about big O before we start. So big O, it's a measure how efficient an algorithm is. So how efficient is an algorithm? It's just a shorthand notation, so it makes it really clear how efficient an algorithm is. For example, with a linear search, if you've got a list that's 10 items long, you might have to go through all 10 to find what you're looking for, and it might not be there, but on average, you have to go through half the list to find what you're looking for, because it could be in the front half, could be the back half. On average, it's around about the halfway mark, if it's there. Okay, and if you've got 100 items, you might need to go through 50 items. Okay, so for linear search, if you 10 times the amount of data, you go to 10 times the time to process it. Okay, so if we had a list 10 items long, we're going to need to let through the list. We need to go through 5 items on average. 5 items on average to find the item we want. So 10 items in list. We need to do 5 loops. In other words, start at the first item, then go to the next item, then go to the next item, and so on. And if we go to 100 items, we need to go 50, because on average, it's going to be halfway through the list. Okay, so you can summarize that with big O notation. And big O, so linear search, you said to have a big O of n. Okay, in other words, it's linear. If you double the amount of data, you double the amount of time. If you quadruple the amount of data, you quadruple the time. Okay, so that's linear search. We're all okay so far? I hope that's not too bad so far. Now, when you start getting into sorting and compression and encryption and all those sorts of lovely things which are all in your future, then the more efficient an algorithm is. In other words, it's the lower its order, the lower its big O, the big O magnitude, more efficient, the harder it is to code. And of course, it's also harder to understand. So there's all these really simple, I think we did some in the prior course. I think we did bubble sort in the prior course. And so we've got really simple sort algorithms like bubble sort, and they're really easy to understand, and they're really easy to code, okay? Certainly compared to the other algorithms, but they've got horrible big O efficiency. So bubble sort, it's got an order of n squared. Okay, so if you double the amount of data, you quadruple the amount of time to process it. Okay, so bubble sort, really easy to understand, really, really easy to code, certainly compared to the other methods, and certainly once you've done it once. But if you double the amount of data, you're going to quadruple the amount of time. So if you're sorting a lot of data, like millions of records, bubble sort, probably not going to do it, you know, and not in a reasonable time anyway. You might need to let it run overnight. Okay, but then you've got other sort algorithms like tree sorts, merge sorts, shorts, sorts. Okay, and they're really efficient. They got really good big O efficiency, but they're hard to understand and visualize. They're complex to code, at least the first time you do it. More complex to code. But you got, if you double the amount of data, you might only increase the time by a small amount. Okay, so they're the sorts of algorithms you want, and you want to collect them as you're going through your. If you want to be a computer scientist and a programmer and a software developer, you want to sort of try and collect the algorithms and make sure you can code them and understand them, which you've got really good big O efficiency. Okay, and it is a challenge. I've been on the lookout for the most efficient algorithms for 40 years, and they keep coming out with more. There's more every day in every area. It's just expanding. Computer science is expanding out in all areas quicker than you can possibly grasp it or understand it. Okay, so I've just got a question there from Kurt. I haven't been able to attend lectures due to work. Is there any way I can access what you went through last week? Yep. So all of my lectures are all on my YouTube. Okay, so if you go to Mike's Java videos, tiny URL, Mike's Java videos, it'll take you straight there, and all the lectures are there. Dozens and dozens, hundreds of worked tutorial questions and exam questions, and build your own software and how-tos, and all that sort of stuff. So everything's there that I do. It's all on my Java stuff. I wish I'd been uploading to YouTube the whole time I've been doing videos to CQ Uni, because I've done so many videos that are uploaded to Moodle websites, and then next term comes around and the next course coordinator doesn't grab the material, and it's erased after 3 or 4 terms, so you lose it. So that's why I do everything on YouTube now. I don't have access to Moodle, and so YouTube's the only place I can upload it. So I don't have access to Moodle at all, because I'm only a part-time lecturer tutor now, so I don't have access to Moodle. It's only the course coordinator that can do that. Okay, so that's a good question, but and also there's searching. We talked about searching, but there's another sort of search called a binary search, and we'll have a look at the algorithm for that a little bit later. Binary search, and it's got an order. It's log n. Okay, and if you've ever done a log graph, if you've ever plotted logs of a number, it goes like this. This is a little graph I'm drawing. And log this linear one here, as you increase one, you increase the other linearly. So it's a nice straight line, straight up. 45 degrees if you're using the same scale on both axes. But log n is a really shallow graph. I don't have enough resolution to draw all the pixels, but it sort of goes like that and then flattens out very quickly. So it goes up and then flattens out very quick, or almost flattens out. It's still rising, but I don't have the resolution here to draw the pixels, so I can't really show you. But, it's not rising like this. This is crazy. You know? And also when you get onto algorithms that order n squared, they're going up exponentially. So they start off here and they follow this axis very closely compared to the order n. Okay, so if ever you want to compare how these things look, put some numbers into Excel and graph it, and you'll see very quickly how they vary. Okay, so it's something like order log n. It flattens off very quickly. So if you double the amount of data, you increase the amount of time by just a tiny fraction, especially when you get to big N, you know, like 100 records or 1 million records. To go from 1 million records to 1 billion records in a binary search might only increase your time by a tiny little fraction. Okay, so they're good if you can find them, those algorithms. Okay, so that's what we're talking about this week. Linked lists and algorithms. And I'm pretty sure we did sorting in the prior course as well. Can anyone confirm that? Wayne or Amy, can you confirm that? Andrew?
Yes, we did.
Yeah, we did this sorting, yeah. I think we even coded the bubble sort just briefly. We'll go over it again today. Look.
I did the prior course 2 years ago. I can't remember.
No, that's right, Amy. You know, fair enough too. Yeah, fair enough. 2 years ago is a big ask, yes. Okay, so don't worry too much. We'll go through it all again today. Don't worry. Okay. We might actually do a bubble sort now. Let's just put down some data and we'll see how it works. Okay, so 10, 5, 15, 45, 56, 7, 18, 22, 6. I'll keep it just the 2 digits. So let's bubble sort this data. So what you do is you take the first 2 numbers and compare them. Okay, and if you want to do an ascending order sort where you got the small numbers first and the big numbers last, then those 2 are out of order, so we need to swap them. Okay, and then you compare the next 2 numbers. Okay, 15 and 45, and they're in the right order for an ascending sort, so we'll just copy those straight down. 56 and 7, they're in the wrong order, so we'll swap those 2. 18 and 22 are fine. And we've got 6 on its own. Okay. Now you can actually do a variation of this where you compare those 2 numbers and then that number with that number. And then, you know, so you're sort of doing it that way. So you could do the first 2, then the second and so the first and the second number, then the second and the third number, then the third and the fourth number. I'm just showing it. Well, actually, yeah, we could do it that way. Let's do it that way. So to compare 10 and 15, they're in the right order. So we just put 15 down. 15 and 45 are in the right order. 56 and 45, they're in the right order. But we need to swap 7 and 56 now. So 7 and 56. And then 18 and 56 are in the wrong order. So we can go 56, 18 and 56. 56 and 22 in the wrong order. Actually, I might go back the other way it was. The other way is a bit easier to understand. Just do pairs of numbers. Okay, so after one pass through, that's what you end up with. So our data's still not sorted, so we need to go through again. So compare 5 and 10, that's fine. 10 and 15 is fine. 15 and 45 is fine. 45 and 7 is not fine. So on the next pass through, when it was 7 there, and then 45, and then we compare 56 and 18. They're not in the right order, so it'll be 18 and 56. And then we compare 26 and 6, 22 and 6, and they're in the wrong order. 6 and 22. Okay, so after 3 passes through, that's what we've got. And they're still in the wrong order. So we go through again, compare adjacent sets of numbers, 5 and 10. They're fine. 10 and 15, they're fine. 15 and 7, they're not fine. So we need to swap the 7 and the 15, and then keep going through, swapping pairs if they're out of order. Okay, so the algorithm for that, we could do it in pseudocode. Let's do it in pseudocode. It's a great way to plan things out and think about things. You don't have to worry about Java syntax and all that sort of stuff. So, let's just loop through. Let's just do one iteration now. Okay. So we've got an array called error. Let's talk like a pirate day. Error. Okay. So we'll go for k equals 0. It's looking a bit Java-ish. K is less than the error.length. K plus looking very Java-ish. Doesn't matter. If error k is greater than the next one. Okay, so if the current element is greater than the next one, so the one at this location, location 0, is greater than the location at 0 plus 1, which is 1, then we're going to swap them. So temp equals RK, RK equals RK plus 1, and then RK plus 1 is equal to our original, which is temp. Okay, so we're just keeping a backup of RK and temp, setting temp RK equal to the next one, the next element, and then we're going to bring that one back in to play again. So RK plus 1 equals temp. So we're just swapping the two values over. Okay, so that'll get you. And also we want to be careful because we're going to the next element. So you want to go -1 for the length. Length right as well. Okay, so that's one pass of the array. Okay, so all you need to do is, if a swap occurs, I'll set swap to true while swap equals true. Okay, so I'll set swap to true, and inside the loop, the first thing I do is set swap to false, and then I loop through the array, and if any swaps occur, I set swap to true. So if any swaps at all occur during that pass of the array, I set swap to true, and then we keep looping while swap is true. Okay, so as soon as there's no more swapping of anything, if we pass through the whole array and there's no elements swapped, we're sorted, so we're finished. Okay, if this is Java, we put curly brackets there and there, and you know what I mean. The indentation means the brackets. Okay, so that's all the pseudocode is for bubble sort. Okay, so a really good task for you to do is to, so students to do, so write the Java code. And then one thing I recommend you do is make it generic. So make it so it can handle any type of data. For example, you might want to make it any type of data that maybe has a compare to method. So for any class that has a compare to. And we did that last week when we talked about our array list class. Remember we talked about having a compare to, and so what does that have to implement to have a compare to? So you might have your bubble sort might go have like this, T, and extends. In other words, it can take any type of data as long as it extends comparable. Okay. So we go back to our generic classes and generic methods we talked about in week 6 and 7, and what we did last week in week 8, week 9. Okay. So a really good thing for you to do. Certainly if you did the course a couple of years ago, maybe, and make sure you get your Summer 2, focus on the Summer 2 first, and then worry about this sort of stuff. But be really good exercise for you to do to get that, to convert that to Java code. We're almost there. It's very close. So maybe get it working for an array, and then change to strings, and then make it generic, so you can do it for any type of data that implements the comparable interface. Then you won't have to worry about ever writing it again. As long as you're working with Java, you won't have to write it again. It'll be there for you if you need it. Okay, any questions on bubble sorts? No questions? So it's one of the easiest to understand. It's really easy to understand in the scheme of things. You might think, oh my God, that sounds pretty complex, but really in the scheme of things, it's really a very easy sort to understand. It's really easy to code. It's like minutes to code. And but if you double the amount of data, you quadruple the time. So if you get onto tens of thousands, you might need to wait. So if you need data that's sorted often, or in a shared user environment where there's lots of users on one server, look at some other algorithm, merge sort, tree sort. We won't worry about coding these. These are a little bit more than we've got time for. Okay. No questions on bubble sort? Okay. So we'll talk about collection interfaces, iterators, linked lists, algorithms, max sort, and binary search. So we've just been talking about sorting a little bit. And so collections and iterators are really, really nice things to have. You can create data structures of things and use the collection interface to make them sortable, and use iterators to step through things. So it can save your code. So there are extra things you need to worry about in Java, extra classes and things you need to worry about in Java, but they can save you a lot of time if you spend just a little bit of time learning about them. Okay. Then we'll come on to linked lists, which we haven't done yet. Then we'll talk more about algorithms. Follow this discussion on. So collections and interface in Java. It's a fundamental interface for collection classes, so array lists, linked lists, stacks, queues, trees, those sorts of things. Amongst many methods of the collection interface, the following two are very useful and fundamental: the add and the iterator. Okay, so if you've got a class collection, so if you've got a public class implements collection, then part of your contract is that you need to provide implementations for the methods that are listed in here in the interface. And two of the most fundamental ones are the add and the iterator, but there's other ones as well. Okay. A lot of the classes you use in Java, or we will be using in Java, like the linked list class, that's already got these things built in, so we don't have to worry about building them ourselves. Okay, but when you build your own classes and you want to implement the collection, you need to implement those methods inside here. Okay, but there's add and iterator, and there's many others. So the add method adds an element to the collection and returns true if adding the element actually changes the collection, otherwise false. So it's a Boolean method, it returns a Boolean. Okay. And it returns true if the collection was, if the add was successful, otherwise it returns false. An iterator method returns an object that implements the iterator interface. So that's another interface in Java. One of my interfaces left, right, and center now. And we'll talk about a little bit more coming up. And the return object can be used to visit the elements in the collection one by one. So the iterator helps you step through your collection. And you might be thinking, well, with what we've done so far with arrays and array lists, we don't need any of this, and that's true. But we're coming on to other data structures now, where we can store data maybe more efficiently or more in a more useful way. Okay, so we're coming on to other types of data structure now. And then the iterators and collections become very useful. So here's the iterator interface. Okay, and there's methods called next, has next, remove for each remaining element. Okay, so that's a iterator version of the for each loop. Okay, so we've got the next method that visits the elements in the collection one by one. If the next method is called at the end of the collection, then it throws a no such element exception. So it's got exception handling built in, and some of these methods can throw exceptions. The hasNext method has to be called before calling the next method to avoid the above mentioned exception. So you say if hasNext, we're sort of so this is just a skeleton of the code, it's not complete. So you declare sort of like a list object called myList maybe. Okay, and then you say myList.hasNext. Okay, so you can do it like that. That means if hasNext is true, or you can make it really clear. I like putting the really clear part in and saying equals true. So if there is a next element in the list, then you can say myList.next. And that moves you to the next element in the list. Okay. To inspect all the elements in a collection, do the following. You request an iterator object, and then while hasNext method keeps returning true, keep calling next, and that takes you through the whole list. Okay, so it's sort of what we're doing here. Sounds pretty complicated, and it is a little bit hard to get your head around at first, but when we work with linked lists and queues and stacks and things, you'll appreciate what these two interfaces provide. Okay, so there's some more complete code here. We've got a collection of strings called C. We declare an iterator based on our C object, which is we call it with C.iterator. That creates the iterator, sets it up. So iterator based on the string class iter equals C.iterator. So there's no new. You don't say equals new iterator or anything like that. You just say equals C.iterator. And then it's the iterator you use here. So while the iter.hasNext, so it's this object, your iterator object. While iter.hasNext is true, then you can get the next object, iter.next, and so on. Okay, so you can see why I was calling it the skeleton here, because there's a one step missing where we create our iterator. Whatever that is whatever you say here. myList.iterator. It's actually this iter object that you use to step through your list. That's sort of that sort of thing how it goes. And if you want to get the element out, you say iter.next, and that returns the element as well. So it's not just moves you to the next element, it returns the value of it as well. So if it's strings you're talking about in your data structure, the element returned by next is a string. If you're dealing with employees, what the next returns is an employee, and so on. So it just depends on what data you're storing here as to what you get out. Okay, so iter.next. Generally, C call iter, and C's single letter variable on its own is horrible. Let's go back to the early days of computers. So I'd probably try and avoid that. I'd probably call it something a bit more meaningful in C. But iter, why not? If you had lots of iterators declared, you could have iter for my employees linked list. You could have iter, iter employees linked list. So you make it really clear which one it was. So Java iterators can be presumed to be occupying the space between the elements. So if you've got these elements here, so at the start, the iterator's here before the first element. So say if has next is true, it looks ahead and says, yeah, there's one there. So you go next, and it jumps you here, and next it returns the value behind it. Okay. Then you go. Then when you're here, you say if has next is true. Yep. So there's the next element here. So you go next, and then that returns the value behind it. So you're always jumping ahead and returning the one behind you. Okay. That's why you got to say if has next is true before you call it. So when the next method is called, the iterator jumps over the next element and it returns a reference to the element that it's just passed. So it's sort of looking backwards a little bit, if you think of it that way. The remove method, the interface removes the element that was returned by the last call to the method. Okay. By the last call to the next method. So whatever you called for the next method last is the one that's removed. Okay, so we've got a list, a collection of strings, whatever they might be, some sort of data structure of strings, and we create an iterator on it. We can say it.next, so that jumps over the first element, and we now return the value of the first element, but we haven't done anything with it. We can say string whatever equals first, equals that first one. Then we jump over the second one, and look back, and that's the value it's got. Next, let's return that one. And if we say iter.remove, it removes that one. Okay, so they're all these methods are sort of looking backwards. They're going to remove the one that they just jumped over. Pretty strange way to do it. That's the way they've done it. You can also think about it going ahead, but then you run into danger when you go id remove, because you might be thinking it's going to remove that one when really it's, yeah. So it's better to think about looking backwards. And all the textbooks and things in Java are written that it looks backwards. So I try to think about it looking forwards for a while, and I said, no, everything's written to look backwards. So just change the way you view the structure. So the remove method call is always preceded by a next method. If you try and call remove straight up, it's an error because you haven't jumped over the first item yet. So it.remove can't remove anything if it's at the start of the list. And this one's okay because you've done a next and then a remove. Ideally you should call. Okay, Kurt. No worries. We calls poor Kurt. Okay. So it.next is fine because you jumped over the first one and looking backwards, and then it.remove removes the first one. So that's all fine. And this here, you cannot call remove twice, because once you've removed an item from the list, there's nothing there to remove again. So if you go it.next, it.remove, it.remove, it's not okay because you've already removed that element. Okay. So if you were up here at the time you called that it.remove, it removes that one, but it doesn't spring back to here. Okay. So it's still there and there's nothing to remove. Again, strange sort of stuff. It does feel strange the first time you see it, the first time you work with these things, or even the first, second, and third time. So if you want to remove the first two elements, you clear your iterator, it.next, it.remove, that removes the first one, it.next, it.remove, that removes the second one. So if you want to clear it the whole list, you go it.next, it.remove, it.next, it.remove, while has next is true. just the way you got to work with them, I'm afraid. That's the way they've coded them in Java. Of course, if you're not happy with this way of working with general collections of whatever they might be, you can always write your own if you wanted to, but it's a shame when there's pretty good classes already built into Java. Okay, so the for each version of the loop that the iterator interface provides, or you need to provide if you're implementing iterator. And that should be able to be called with a lambda expression, just like you can with your normal for each loop. Okay, so prior to Java 8, let's not worry about that. We use the iterator and lambda. So lambda again helps us. So we've got a collection of something. We don't know what it is. Could be a linked list, could be a tree. We don't know. Declare an iterator based on that collection of data, whatever it might be. C.iterator. Iter.hasNext, or iter.next, and then iter for each remaining element, and then print it out to the screen. That looks really strange. The old way to do it, while iter.hasNext is true, get the element out of the collection and jump to the next one. Get the current value and jump to the next one, or jump over the whatever and return the value of that previous one is the way you've got to think about it, and then print that out to the screen. That's actually a nice way to code it, I think, in the end as well. That does look strange with the we're not actually referring to the iterator in here. We're not actually saying get me an element or whatever. Java knows you mean this iterator because you're calling the for each remaining with that iter dot. So it does look a bit strange when you see that. I'll try and use the collection word now because it could be a collection of data. It doesn't have to be a list. It could be all sorts of things. There's all sorts of crazy structures out there. Okay, so you create your list and your iterator. And while iter.hasNext is true, whatever our data is, strings or employees or whatever, element equals iter.next, and then you could system.out.println it to the screen if you wanted to. Whatever you want to do. Okay, so you got the element out of the whatever it is, the collection. If you want to erase the entire collection, erase all elements in the collection. And it's a similar sort of loop. There's other commands we haven't covered yet where you can reset the iterator pointer back to the start of the list and all that sort of stuff. They haven't mentioned those in the slide yet, so I'm not going to confuse things by adding yet more commands. Okay, so let's just start with a fresh list again and create an iterator. And so that's how you'd erase all the elements in the list. Okay, so you start with jumping over the first one and then remove it, and then jump over the second one and then remove it, jump over the third one and remove it, and so on. Okay, until hasNext no longer returns true. So pretty strange way of thinking about things, and it's going to be quite scary for you, I think. But we'll do a few examples, especially in the tutes. There's some really good questions in the tutes, which will get you comfortable with these things. So don't worry. Confusing.
It's very confusing.
It is very confusing. Don't worry, there's plenty of help available. There's some good tute questions coming up in the tutes, so don't worry. Okay, all right. Now, linked lists. There. So I've done a whole lot of videos on linked lists. I've got a video here where I talk about reference data types, and then I do a very, very gentle introduction to linked lists. Okay, so that's a video there you can look at. I've done another one where we actually build a linked list from scratch, and there's part 1 and part 2. And another one where I talk about arrays, linked lists, and iterators, where I'm answering an exam question and sample exam. Another one where I build a GUI based on a linked list, and you're adding and deleting and displaying data from your linked list. And there's multiple parts to that, part 1, part 2. I think there's part 3, 4, 5 as well. Okay, so definitely start with those if you like. They're definitely a good place to start. We'll go through things just briefly here as well. So remember when we created an employee Mike equals new employee, whatever we need to provide for the constructor. And if we say employee Frankie, new employee, and whatever we need to provide, I'll put some data in, make it look a bit nicer. Two employees there, okay. So Mike's got his own area memory where that data's stored. Frankie's got his own area memory where that's stored. If I say Frankie equals Mike, what happens?
You take Mike's array, not array, God, what am I talking about? His memory reference and put it into Frankie's.
Exactly right. So they're both now got the memory address of this data. Okay, nothing's referring to Frankie anymore. They're both referring to this data. Okay, so if I say Frankie dot set name Fred, which data will I change? I'll change Mike's name, won't I? Because they're both referring to Mike. So this data, Frankie. So that'll change to Fred. Okay, because they're both referring to Mike's memory location. Okay. So keep that in mind, because that's an important part to understand linked lists. So what's a linked list? It's a collection of pieces of data in memory, where each piece of data knows about the next piece of data in the collection. So it doesn't know about what's beyond that. All it knows about is the next bit of data. Okay, it doesn't know how many bits of data are ahead or whatever. So it's sort of like the concept of a node, which is some data, as much as you like. You could have video data, of employee data, whatever you like. as much data as you like, and a reference to the next node in the list. A linked list then is a collection of nodes. Sounds pretty complex. They're really quite easy. Once you've done them a couple of times and you've seen them, you've built one from first principles. They're really quite easy. Let's see if we can build a node just to contain a bit of data and what might know about the next bit of data in the list, with the location of it. So we've got public class node. We've got private string name, whatever, or whatever you want to store there. You can store as much data as you like in a node. It doesn't matter what it is. For most examples you see in textbooks, it's just one bit of data, but it could be anything. And these could be arrays or array lists or anything you like as well. Okay, so it's data in a node. And then how do we store a reference to the next node in the list? Okay, so how do we store a reference to the next node in the list? We've talked about this a little bit in the past. So we've got a node object, and we call it next node. Okay, so what sort of class is this when it's got an object of its type, of its own type? We had a special word for that in the prior week.
Recursive?
Almost. Self-referential. In other words, it's got an object of itself inside there. Okay. So we could create a node. Imagine we had a constructor, public node. We just have names in there for now. Okay, so we'll take out everything else. Just have names. So we've got a constructor that takes a name. Okay. Sets the next node to null. And then we've got a public method, void set next node. So we've got two methods in our class. One's just a constructor, and the other one's a set. We can have more methods as well, but I'm just showing you just two methods. We could have many methods, okay? But I'm just showing you just the two you need. And then we've got a set next node method. Okay, and that takes a node, which is this data type, and sets the next node equal to the one you passed in. Okay, you might have more methods as well. ToString and all sorts. Okay. So how can we work with nodes? Okay, let's declare some. Node n1 equals new node. And I'm going to store Mike there. And node n2 is going to have Wayne. And node n3 is going to have Amy. And node n4. Just a sec. Okay, back again. And Demas and Andrew. Let's put it. I want to involve everyone. So 1, 2, 3, 4, 5. Let's involve everyone in the class. And Kurt's got an honorary node, but he's not here at the moment. So how do we link these two together? We've got this set node method. So let's go n1.set next node to n2. So node 1 now knows about node 2. It knows about the memory location of node 2. Okay. n2.set next node to n3. So node 2 now knows about node 3. Okay. Node 1 doesn't know about node 3. Node 1 only knows about the next node in the list, which is node 2. Node 2 knows about node 3, and so on for the other ones. Node 3 knows about node 4, and node 4 knows about node 5. Okay, and then let's pretend the list ends then. So node 5 would have the next node of null, which is the original value. Nothing's been changed. We haven't called set node. Haven't called set next node for node 5 yet. So how do we loop through all the nodes of data? What about we do this? While I'll go next. I won't call it first. Next node. So the next node in the list, we'll start with the first one, or current, whatever you want to call it, current. While current equals current, set current to N1, and we want to try and loop through while current dot get next node. We're going to have the next node method as well. Get next node is not equal to null. So we want to get next node public get next node. It's just going to return the value of next node. So now we've got an extra method in there, set next node and get next node, just returns the value of next node. Okay, so while current.get next node is not equal to null, we could system.out.println, say curr.get name, and get out a get name method into here as well. Just returns name. Return. So we can get the name out of the class and display it to the screen, and then go curr equals curr dot get next node. Okay, so whatever the current node's next node is, we're going to set to the current node. Okay, so we'll start with N1. And so curr is N1, so we'll get N1's name, and we'll say current equals N1 dot get next node, which is node 2. So now current points to node 2. That's current's the next node to node 2 is not null. So we'll say node 2 dot get next name or get name. Okay, and then current equals N2 dot get next node, which is node 3. Okay, you see how it works? And so with a little loop like that, you can work through your data really quickly. Just wherever these nodes exist, they're not contiguous in memory like an array. They're just anywhere in memory, and we're just stepping through the data because we know where the next bit of data in a series is. Okay, and that's a linked list. That's it. So it's a simple little class. Usually with just a piece of data, but it could be anything. It could be arrays and array lists of data, and it could contain other linked lists and all sorts of things. Could any data you like, and then a reference to the next node in the list. Okay, and just some simple methods: get next node, set next node of the basic 2, and then just getters and setters for your private data, whatever you're storing here, and then a constructor or a couple of constructors, default constructor, parameterized constructor. Then you can just work through them really quickly just with a little loop. Okay, so you got a node class, and then generally what you do is you create a linked list class to handle the looping through all the elements and saving them to file, loading them from file, all that sort of stuff. Okay, so a generic linked list class is what you want. Okay, so I know you've never seen one before, probably. Maybe some of you have, but maybe you haven't. Most people probably won't have seen a linked list before, but is that okay? Is it confusing? Is it horrible? Super frightening? You'll need some time to understand it, get your head around it. Okay, but it all comes down to these ideas. That's what it all comes down to. So You're keeping track of the memory of the next node in the list, you know, where that bit of data is. And that next node knows about the next one in the list until you find something that points to null, and then there's no more nodes. Okay. So it's just applying these principles here. Okay, so what we looked at above is a singly. Singly doesn't look right. Singularly. I don't know. I need help. Okay. Singly linked list. You can only go one way. Okay, so you can only go one way through the list. Just one way through the list, because this current node only knows about the next node. Okay, it doesn't know about the prior node. Okay, if you change things slightly, so if you change your class so that you got a previous node, okay, so next node, prior node, or previous, whatever you want to call it, and you got a set prior node and a get prior node classes. Okay, so if you add two more methods in, set prior node and get prior node, then you can also set up the prior node links down here as well. So n2.set prior node to n1. I'll do that down here. So you can go into set prior node to node 1, N3 set prior node to node 2, N4 set prior node to node N4, and N5 set prior node to node 4. Okay. Then you can start at the back. Get prior node, and get prior node. Okay, so now we're going through the list backwards. We're starting at the far end and we're going through the list backwards. Okay, we can go through it forwards in the original way, and we can move through it backwards by setting node equal to the last node. Okay, and that's all linked lists are. Just chunks of data, and each chunk of data knows about the next item in the list. Or if you've got a doubly linked list, doubly, double E. None of those look right. That doesn't even look right. No. Anyway, if you've got doubly linked list, then you can go forwards and backwards through the list. So you've got the next node and the prior node. Okay. Sounds really complicated, maybe, but if you watch these two videos here where I build it from scratch, and that introductory one, it goes over what I've just. Doubly's right. Is it okay? Thanks, Wayne. Okay, looks strange. English language is a terrible thing. And
Java's not much better, can I say?
Oh. At least Java's got a limited set of commands and don't have past tense and future tense and all that.
This is true.
And let's change it and make your own.
Well, yes, you can always make your own. Yes, yeah, and you can also make your own language. You translate into Java and then compile Java, and then you can can run whatever language you like. But so watch those 3 videos. I'd highly recommend that. You'll really understand linked lists and build it yourself as you go. These ones are build it as you go as well. So follow along and build it. Okay, back to the slides. So a concrete collection class in the Java library. So there's a linked list class built into Java, and it's a doubly linked list. So you can use it as a single or a doubly linked list. It's all built, nothing to do. If you want to create a linked list of employees, you can do it from first principles. And I highly encourage you to do it from first principles at least once. But later on, you can just go like you can with array list. So with array list, you've got add and get and remove and all those methods that we've been doing, and set. All those methods we've been doing with array lists. Linked list. Guess what? It's plug-in compatible. The methods are the same. Okay, so if you've got a project you've done for array list in Java, and you need to change it to a linked list, all those commands are there. There's also linked list commands like next node and prior node and all that sort of stuff. But they've also provided those nodes commands, so you can just use standard array list commands. Okay, and add means add a new node. Get means get the value, get the current node, whatever it might be, an employee or whatever. Remove removes the current node and fixes up the plumbing so that the node after the one being removed points back to the one prior to the one being removed, so it fixes up the plumbing between the links. It's like connecting batteries with bulldog clamps, but car batteries, and you've got bulldog clamps, and you're removing a battery, but you've got to plug it onto the next battery and link them back across. Okay, so it takes care of all that for you, and the set command to change the value of that node, whatever. Okay, so really easy to do. So if you got your assignment 2 is working for array list, you should just be able to change the linked list like that. And nothing to do, nothing more to change. But I highly recommend you build your own at least once, and then you'll understand exactly what's going on with the Java code. And if you have any issues or troubles, you'll understand more what the Java code's trying to do, what the Java library, what the Java class is trying to do. So the linked list implements a collection interface, an ordered sequence that allows efficient insertion and removal at any location. So linked list in Java implements collection. Okay. And so an array stores object references in consecutive memory locations. So you've got arrays, and that's consecutive. At least for the references. And array list is the same. It's consecutive memory references for the data, but the data could be anywhere. The reference could be any location in memory if you're storing employees. So don't need to be contiguous employees in memory. They could be anywhere in memory, but the array, it's an array behind the scenes here. But linked list data could be anywhere, and the memory addresses could be anywhere. So each link also stores a reference to the next in the sequence. So when you've got a linked list. And in Java, all linked lists are actually doubly linked. So you've got one singly linked if you like, just use them single, or double if you want to go backwards and forwards. It's all built in to handle either. And you've got the list iterator interface, and linked list takes care of all this as well. And so there's next, has next, remove for each remaining element. Okay, in the iterator, and then list iterator has add previous and has previous, and so on, a whole bunch of other methods as well. So the list iterator add method does not return a Boolean. The collection method returns a Boolean, but this add method is void over here, so it doesn't return a Boolean. So a bit strange way they've made some return Booleans and some not. The previous method returns the object that is skipped over, and the previous and has previous methods can be used to traverse the list backwards. Okay, so like I said, you can use just these sort of standard commands to work with a linked list, or you can use the actual more linked listy type commands like previous, has previous, next, has next. Okay, if you want to work with it in more of a linked list sort of way. So there's a picture of a doubly linked list. It's like two sets of battery clamps. One's pointing forwards, one's pointing back. Each one's got a thing. And if you think about like swinging on vines in a jungle, you've got two vines, one in each hand. And when you swing to the next vine, you let go of that one and you grab another one. Okay. And then when you swing forward again and you want to let go of this one, grab another one. So that sort of thing, moving through the linked list like that. So one of the pointers is pointing forwards and one of them is pointing backwards, the prior nodes. Okay, and you might have first node here, so you know where the first node is, and you might have last node, so you know where the last node is. You might keep track of those so you can quickly jump to the end and move backwards, and jump to the start and move forwards. And you might have a node count, and so this is the node classes. Node class down here, and this is a linked list class. So you might have a whole bunch of stuff up here to help you move through the linked list. But like I said, there's a linked list class in Java that provides it all for you. Okay, so if you want to remove an item from a linked list, you got a list of strings called staff equals new linked list. Okay, and staff.add. So just like working with an array list, isn't it? And then we create an iterator over our linked list, which is staff.iterator. That's a spelling there. String first equals iter.next. String second equals iter.next after that. And iter.remove to remove the last visited element, which would be this number 2 element. Okay, so the command's the same, but you might need to use iterators and things to get access to them. So not quite as straightforward as using an array list, but pretty close. To convert a class across from array list to linked list is really not a hard task at all. Adding an element to a linked list. So this is where you're going to do your battery clamps. So let's say we've got this bit of data down here we want to add. So this node's next node was that one. We want to now point it to the new node. Okay, so we say node 1's next node is now the new node. And whatever this was pointing to originally, we want to say this node's next node is that one. Okay, so you've got all this bits of data to keep track of. So you want to keep track of what this node's next node was, and set this node's next node to that one, and this node's next node to the new one. So we're getting the forward references right. Then you want to do the same with the backward references. So this node's prior node was that one, but now it's this one. But this node's prior node is our new node, is what this node's prior node was before. So this node's prior node is that one now, when before it was this node's prior node. Okay, so you've got these battery things. I always think about it with bulldog clamps going on the batteries, and you're just fixing up the connections and clipping things on to make it right. That's what works in my head, but you might need a different analogy. I don't know. Vines is good too. People swing on vines. Okay, so if you want to insert a node after Amy, you go iter.next, iter.add. Okay, so it's still the add command, but you've got to use it with an iterator. So the set method replaces, it's like the set method in an array list. The set method replaces the last element that is returned by a call to next or previous. Okay, so a linked list again, start string old value is iter.next, so that would return Amy, and iter.setMary would put Mary there where Amy was. So it becomes Mary, Bob, Carl. Okay, so iter.set replaces the node you've just jumped over. The get method gets access to a particular element. So again, you can use array list notation. Staff.get 0. Once you've got an iterator set up, or that's just a list, so we're just using plain old array list notation there, and that's fine. You can use staff.size and so on to go through as well. You can also use staff.get as well. So staff.get, so get I will return the value of that location. We might have a break. So we'll have a 5-minute break and then come back. So it's 10:13. We'll come back at 10:18. So if there's anything you're not sure about, think of questions if you like, or have a coffee and we'll come back and talk about it. We'll have a 5-minute break. So see you in 5 minutes. We're back. Can you hear me okay?
Yeah.
Okay, thanks, Amy. So highly recommend you build a node and a linked list class from first principles. And if you see my videos there, I'll take you through exactly what you need to do. And we go really slowly. Okay, so and once you've done it once, all the fear and the mystery will go like crazy, and you'll even start to appreciate collections and iterators a bit more as well. Okay, so it helps you understand all of these topics we've covered this week. So here's a bigger example. We've got a linked list called A, and we've got those bits of data in that one, a linked list called B, which has got these bits of data, and we're going to try and merge them. Okay, and so we've got iterator for A called A-iter, and an iterator for B called bitter or biter. While biter.hasNext is true, if iter.hasNext, if iter.hasNext is true, iter.next, and then iter.add bitter.next. So we should end up with a list that has so it's jumped over that, and we're adding the next word from here. So we should have Amy, then Bob, then Carl, then Doug, then Erica, then Francis, and then Gloria, because there's no next after anymore in A after that. So this is merging the two lists together, just putting one word from each after each other. Okay. I recommend if you do write this code, have also if biter.hasNext is true, because this list could be shorter than that one. Okay, this is okay for this example. And then we'll remove every second word from B. So while biter.hasNext is true, create the iterator again. So this is how you refresh the iterator to point back to the start of the list. You just say b.iterator again. That makes it back to the very start. And biter.hasNext is true. Move to the next one. So in other words, skip over the first one. And if biter.hasNext is true, jump over the second one and remove it. Okay, so you're doing two nexts, and one remove. So you're deleting every second node from the list. And I showed you that code before to remove all the items where you're traversing through the list and removing them. There's also a remove all command. Of course there is. Okay, there's other ways to do it as well. If you want to remove everything from a list, just set it to null. A equals null, and it deletes the reference to it, and Java garbage collector cleans it up. But, this is a cleaner way. Remove everything, do it properly. Okay, so just a bit of code to work with linked lists, merging them together, deleting every second element. So if you want to print all the elements in the list, just go print line B, and the linked list class has a toString method that's called, and it just displays the values of the nodes. Go to the screen, and same down here. So print line A. So you don't have to worry about looping through and print lining. There's that class built in, that method's built into there with a toString method. So that's all we do on linked lists. Unfortunately, it's not required in the spec. And really, I think you got your hands full enough probably with doing. If anyone's doing a generic array list class, which is what we did last week in class, we spent the second hour of the lecture on, or most of the second hour of the lecture on building a generic and array list class with a GUI and an interface and all sorts of things. If you've done that for the assignment 2, you've already done more than enough, I think, but not used in assignment 2. Sorry, that probably scared people. Node used in assignment 2. No, it's not. It's not used in assignment 2. Sorry. If you've got multiple array list class, that's fine for assignment 2. If you've got a generic array list class, you'll save yourself a lot of code, and well done. Okay, a bit more on algorithms. So finding the maximum in an array. If A is an array of whatever, if A.length is equal to 0, we could throw no such element exception. If we should also check if A is null. So if A is equal to null, throw an exception as well. And then if it's a generic method, we could say T largest equals A0. There's an equal sign missing there. So the largest value is equal to the first element in the array. And we can loop through from 0, or even better, loop through from 1 onwards, because we've already checked the first element. So loop through from 1 onwards, and if largest or compared to A is less than 0, so the largest is less than that one, then we've got a new largest. So largest equals AI. Okay, so that's finding the maximum in an array, and not bad code. It's missing an equal sign. I'd also check if A is null before I check the length. If A is null or length is 0, throw an exception. That's sort of fine for code. And what sort of order big O would that have? Or even just think, would it be linear? If you double the amount of data, would it be double the amount of time? If you double the amount of data, would it be quadruple the amount of time? How do you tell?
I feel like it'd only have to go through it once, so it'd probably just be n.
Exactly right. Exactly right. So you look at your loops. You've only got one loop. So this is slide 19. Find.
I feel like I'm not seeing what you're talking about. I can still see listing 9.1 linked test.java. Slide 18.
Okay, you can't see slide 19.
I can't. I don't know about other people.
Amy, can you see slide 19?
No, I'm only seeing the listing 9.1 linked list test.java.
I'll stop the video and then I'll start it again. Just a sec. So I'll stop. And then I'll start again. Oh, I might have to do a new share. Maybe I have to do a new share.
Yeah, it'll be the share, not the video.
Can you see it now? Algorithms?
No, nothing's changed.
No, still linked list test.
That should change the whiteboard. Can you see the whiteboard?
No.
Oh.
Ah, sorry. Now we should be fine.
Yeah, now I can
Yes.
see it.
Thank goodness. Oh, and start video. Okay. Okay, so we just so this is what I'm talking about here. So if A.length is equal to 0, throw no such element exception. So we're just doing it generically. It could be an array of integers or strings or employees or whatever. set the largest equal to the first element in the array, so there's an equal sign missing there. And you could loop through, this is starting at 0, you could start at 1 because we've already got the value at location 0, we've already tested that. We're assuming that's the largest. So if int I equals 1, I is less than a dot length. If the largest is compared to that one at that location in the array, if the largest is less than that, it's less than 0, then we've got a new maximum. So largest equals AI. Okay, so there's a missing equal sign there. And I'd also like to see this if A is equal to null or a dot length is equal to 0, then throw the exception. Just check if it's null as well. That's fine. It's pretty good code. So we've got a single for loop. And so that means linear efficiency. Or big O equals, so if you double the amount of data, you double the time. Roundabout. It's not exact, it's just double the time, approximately. Okay, if you've got a loop within a loop, and so nested loops, so you've got a while loop within a for loop, for loops within for loops, or any combination, okay, then you got big O equals O n squared. Little n, big N, doesn't matter. And so if you double the amount of data, you quadruple the time. So these sort of algorithms might be fine if you've just sorting a little, processing little amounts of data, 10 records, 100 records. If you're processing millions of records, you probably want to look at something that's better than order n squared. And if you're doing it many times a day or many times a second, or if you've got many users on a multi-user system, a web server or something, you want to make your algorithms as efficient as possible because things get bogged down very quickly with these algorithms. And then if you've got nested loops, and then if you've got loops within loop, so you've got 3 loops, then you've got big O equals order n cubed. Okay, so if you double the amount of data, you triple the amount of time, quadruple, double the amount of data, you octuple the amount of time, 8 times the amount of time, in other words. Hang on. Yeah. So you basically just put n 2 in there. So 2 cubed is 8. 2 squared is 4. Double is 2. Oops. Finding the... So if you want to do the max for a collection, and looks a bit complicated, so you want to do it so that's only for data types, any data type that implements a comparable interface. So you can say t extends comparable to limit it down, just like we did last week, and then the weeks when we talked about generic classes. And then if c dot is empty, so you can use the isEmpty method. I'd also suggest use, I still use if c is equal to null or c is equal to isEmpty, and there's a missing round bracket there, too much errors in the code. Throw in no such element exception. Otherwise, create an iterator. It's safe to create an iterator now. T.largest equals iter.next, so we get jumping over the first element and pointing back. While iter.hasNext is true, T.next is equals iter.next, and then you compare the two, largest with the next, and largest equals next if they're out of order. And then return the largest. So that's the sort of method you could do for any sort of collection that implemented the comparable interface. Okay, so for example, in our if we've had a linked list class that was using iterators. So again, that's just one loop, so it's order n. Single loop. So, okay, so one of the, you might be thinking, well, there's no real, I haven't seen any real benefit for using collections yet, Mike. What's the reason? And one of the reasons is you can get really easy sorting. Okay. So you've got an array list, string, names, AL array list equals new. And if you want to sort that array list, you can go collections. So part of the collections class is you can sort. List. Done. No need to write any sort code. And the sort built into Java is really quite efficient. So that's a good sort to use. Collections, yes. Most things in Java are singular, but there's the occasional thing that's plural. So maybe it is getting worse and worse. And the same applies to linked lists. So if this is a linked list object, just sort it, and the nodes are sorted. It fixes up all the plumbing between all the wires, does all the cable unclamps and clamps. Okay, so pretty good. If you had an array list of them, exactly, as long as the array list elements implement comparable, yes. So array list in Java does implement comparable, but if you've done your own generic array list class, for example, and you implement comparable, and you've got a compare to method, this works for that as well. Okay, so you've got an array list of employee. Okay. Oops. Again, you can sort the array list by employee, as long as your employee class implements comparable. So you've got a compare to method to compare employees. And you can do other stuff as well. You can actually name. So if you've got a compare to method in your class, how deep do I want to go? So you can actually do stuff like you can name the accessor method that is used to compare objects. So you can bypass the compare to method and sort by something else. You can sort by ID order or something like that. And you can also specify the direction. There's a whole lot of really great stuff you can do. Okay, so you can bypass using the compare to method and use other things, use other methods that are part of your class. So you can just sort in the normal compare to order sometimes, or if you want to get the employees in name order, sort by you can call this sort method with a little bit of extra code here. It's not much code, a little bit of extra code here, and you can say use the get name method instead, or use the get age, or use the get start date, or whatever. Okay, so you can sort employees in very different orders very quickly, very easily. So hugely powerful. So even just on that alone, it's worth using collections, but there are other benefits as well. Okay, but just getting access to this sort and being able to sort by different things really easily is wonderful. So there's doing a reverse order, staff.sort reverse order. And here it's saying, it's overriding what you're going to compare by. And we're saying use a salary to compare employees, not the compare to method or not some other method. We're saying use the salary method. And if you want that reversed, it's .reversed. So a whole lot of strange syntax here. You go reverse order here, but if you want to compare by a salary and get it reversed, you've got to go .reversed. Okay. So if anyone's keeping a little note file with useful snippets of Java code, I recommend you put these sorts of examples in and this one. Keep all these little examples in there because when you want to find these later on, you can never find them when you need them. And so very powerful stuff. When you start working with iterators and collections, you can do this sort of stuff. So no matter what the data structure is, it's an array list, it's a linked list, it's a queue, it's a stack, it's a tree, doesn't matter. Sort it in reverse order by salary. So you get the most highly paid employees first, and whatever. Pretty powerful stuff. Define the position of the searching element in a collection that implements the list interface. You can use a binary search. And I think we did talk about binary search in the prior course as well. So binary search. So data must be sorted. It doesn't matter whether it's ascending or descending, doesn't matter. And what you do is you split your data in two. So if you've got data like this, like Frankie, Andrew. Let's see if the chat shift the chat in there. Demas. And we'll add Kurt in as well because he's here earlier. Hey, George, okay, Kurt. Okay, so that list is sorted, ascending, and a binary search, you go to the middle element. So let's say we want to find out if let's see if we want to find out if Hope's in the list. Okay, so we compare Hope to the middle element. Okay, and Hope is less than Frankie. So we then focus on this top half of the array, and we split it in two, and we compare Hope to Bella. Okay, Hope's greater than Bella, so we then focus on this little part of the array. We split that half of the half in two again, and focus just on that part. So we then check the middle of that array, which is Bogle, and which isn't Hope, so it doesn't exist. And so we're down to one element. We can't split that in two, so we can return false that Hope doesn't exist in the list. So binary search is all about splitting your array in two, splitting your data in two, and again and again until you run out of data or you find a match. That's what it's all about. So if you've got 1 million records, you jump to the middle of those records, the 500,000th record, and check what you're comparing, what you're searching for against that. And if it's greater than, you divide that 500 to 1 million records, you go to the middle of that, which is 750,000. You go to that middle point and then compare. And if it's less than, you go to the 500 to 750. Or if it's greater, you go 750 to 1 million and split that in two. Just keep splitting in two. So it converges very quickly. Answer very quickly, super fast. When you've got a large amount of data and you compare binary search and linear search, binary search is just so much faster, especially when you get to big amounts of data. So there's just one slide on binary search. I think we did talk about binary search just briefly in the prior course as well, but binary search is actually another reason to use collections because it's built into the collections interface. So if the collection has already been sorted by compare to, then you can say int I equals collections.binarySearch C, that's your collection, and your element you want to search for. It might be an employee, it might be a string, might be something, whatever. And this will return the index of that location, index of that element in that location. And -1 means not found, or 0 or greater means it was found at that location in the linked list or array or whatever it is. If the collection has not been sorted by compare to of the comparator interface, a comparator object also has to be specified as an argument. Okay, so if you haven't sorted by compare to, then you've got to provide some sort of method to compare to here. You might say get name, and it's this sort of notation here: employee get salary or employee get name. Is that sort of notation that you put there. So you specify the comparator, and then then it will do the search, the sort, and then the search as well. So Java will take care of all that for you. Pretty powerful stuff. If the element is being searched in the collection C, a non-negative return value specifies the position. So if it's -1 or less than 0, not found. If it's 0 or more, it was found at that location in the whatever it was, array list, linked list, whatever it was. So two good reasons to use collections. You've got the beautiful sort, and also you can sort by anything you like, any order you like, ascending, descending, by any method, using any method really quickly. Just specify whatever you want to sort by. And you can also get access to this binary search, which is really, really good as well for doing searches. There's at least 2 good reasons to use collections. So in assignment 2, it doesn't say, of course, it doesn't say, but if in assignment 2, if you had a lot of vehicles and you wanted them sorted by registration number in one of the combo boxes, you could do that pretty quickly with a collection and sort that list by license number or whatever, license plate number. And if you want to display a list of owners and you want to display them in maybe ID order sometimes and alphabetical on last name other times or whatever, you can do that really easily with collections. So don't have to worry about having multiple sort methods or whatever to use different comparators. Okay, so if you need the data in different orders, so if you need them by different orders, it might be worth looking into collections. Okay. Now, if it doesn't say that in assignment 2, and we're generally only dealing with 3 or 4 records of each, so you definitely don't need to worry about this for assignment 2. But if you want to have a go, you know, if I was a marker and I saw someone using collections for assignment 2, I'd say, oh, wow. Okay, wow. I'll be thinking bonus marks already. Okay, but I'm not marking, so I can't say. So that's it for this week. Have we got any questions before we go? Any questions? Everyone's okay? So like I was saying earlier, I highly recommend you go through those 3. Although I understand people are probably focused on their assignments and they probably won't get to these. But if you're worried about linked lists, work through those and all the fear will go, hopefully.
So this isn't really related to what we did today, but kind of what we did last week.
Sure.
We talked about using the typed files, the serialized files, and generics.
Yep.
So when I try and use the read object and then put that into a generic array list, it works, but it throws a warning about unsafe operations. I'm guessing because you can't guarantee what sort of object you're pulling out of the file or any of that sort of thing. Is there any way to make that not be an error, a warning?
Okay, so let's just have a look at our code from last week. Let's have a look at our code actually. So with your read object file, so that wasn't here. So read object. So what can you do? I wonder if that will help. So whatever T is, employee or whatever, we're going to typecast it to that. I wonder if that will help.
Yeah, I did that. It still throws a warning.
That's one. And you, I mean, instance of. So this I'm reading it as an object here, and then I'm converting it to a vehicle. So I check if it's an instance of, and then do a typecast.
Okay, I didn't do that.
And that stopped the warnings. No more warnings after that. Okay, and you can do it all in one line of code if you wanted to by saying this. So all in one line of code. Vehicle equals vehicle object. That should be fine. But it's also always a good idea to do that instance of check as well, especially when you're reading from a file because you don't know what's coming in. Someone could have told you to read the owner's file and store it in vehicles. So yeah, I think that's probably a good way to go, a safer way. Do the instance of check as well. And if it's not an instance of vehicle, throw an exception. Something bad's gone wrong. Either the files are corrupted and mixed up, or someone's trying to read vehicles into owners, or something's wrong. But, okay, that sort of code there should fix it. Everyone else okay?
Okay, thank you.
That's all right, mate. No worries. No worries. Everyone else okay? Any other questions? I realize this stuff's going to be pretty scary for you, and we're looking at some pretty scary looking notation here. But when you can appreciate the power of it, you can provide any method in your class that returns a value can be used to sort the data. I mean, you can sort by salary, by name, by whatever you like really quickly, or just do a sort and it does the compare to method automatically. Pretty powerful stuff. Okay, well, that's it for this week. Thanks for coming along. Thanks, Amy and Andrew and Wayne and Kurt. And Damien's there too. Sorry, I didn't realize there's more people. Nicholas is there. Hey, Nicholas. Thanks for coming along. And see you next week. Good luck with your assignments and see you next week.
Thank you.
Thanks, Mike.
Thanks, Wayne. Thanks, Amy.